Okay, let's start. So welcome everyone, and nice to see many people here, although we can't see you, but I see your names popping up. I have the pleasure of introducing today's speaker, Watse Sybesma, who will talk about the Nobel Prize in Physics 2020. And this is a talk sponsored by the Vísindafélag, the Science Society in Iceland, as well as the Physics Society, the Eðlisfræðifélagið Íslands. And as you know, probably it's part of the series on the Nobel Prizes that is given annually by the Science Society, and this is the second talk this year. And at the end, I will put up a slide on next week's schedule. But for today, I will introduce Watse Sybesma. He was born in 1989 in the Netherlands and obtained his PhD at the University of Utrecht in the Netherlands, where he worked on black holes and related topics. Recently, he has obtained a grant from the Icelandic Research Fund to further pursue this line of research at the Mathematical Physics Group of the University of Iceland as a postdoc. And interestingly, in addition to his science research, I noticed he has also published a children's book on black holes. So I think he's very well equipped to discuss the topic for a wide audience. So Watse, please.
Thank you, Christian, for this kind introduction. Yeah, well, let's hope it will be as easy as a children's book. So first of all, I'd like to thank the Eðlisfræðifélagið and also Vísindafélag for organizing these lectures. I went to the last one about medicine, and I learned a lot about some disease with a C. And I hope you'll learn a bit about the formation of black holes and the supermassive object at the center of our universe, which is very much the title of the Nobel Prize 2020. Furthermore, I'd like to acknowledge the University of Iceland and RANIS, the University, the Icelandic Research Fund for making my own research possible. All right, so what we're all here for is the Nobel Prize. And this year, it was split into, two topical halves, which were given to 3 people, which is the maximal amount of people that can share the Nobel Prize of Physics. So let's go to the first half. So the first half is given to Roger Penrose for, in the words of the Nobel Academy, for the discovery that black hole formation is a robust prediction of the general theory of relativity. So Penrose is a theorist at the University of Oxford. The other half of the Nobel Prize went to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. So these are astrophysicists who make very, very detailed observations of our universe. So this talk is organized in the following way. I'll start, to sort of tell you some basics about gravity, and then slowly we'll go to the topic covering Roger Penrose, and then halfway through we'll continue with the topic covering Reinhard Genzel and Andrea Ghez. And one thing I'd like to sort of emphasize is that what I really like about this year's Nobel Prize is that it really shows a synergy between, on the one hand, theorists, and on the other hand, astrophysicists who really observe our universe. But first things first, Newtonian gravity. So gravity is the thing that makes you fall. It's the thing that makes us stick to the surface of the Earth. And there are two basic rules of gravity which I'd like to, well, remind you of. So the more mass gives more attraction, which means that if you go onto a scale on Earth, it will give a different number than when you go onto a scale on the moon, purely due to the fact that the Earth is more massive than the moon. So that's the first point. The second point is gravity becomes weaker as you go further away. So you might remember all these kind of videos or just science fiction of astronauts going into space, and as soon as you sort of left the Earth behind, everything goes hovering. And that is a reflection of the fact that the Earth's gravity or the sun's gravity or any gravity is unable to really influence you. So, okay, let's go over three sort of examples. So the first one obviously is falling. So it's an apple. If you drop it due to its gravitational pull with the Earth, it will go down. So now you can wonder, is there a way that I can actually beat the gravitational pull? And yes, you can. For instance, if you own a rocket. If you own a rocket, and if you then go at least 40,000 kilometers an hour, you're able to escape the gravitational pull of the Earth. So it also happens that the circumference of the Earth is 40,000 kilometers. So it means that the amount of velocity or speed you need would also be able to get you all around the Earth in 1 hour. And then there is another sort of feature of gravity which we are aware of quite often, and that's orbits. So if some object, let's say the moon, has some angular velocity or has some velocity which is not directed towards the Earth or directly away from it, then depending on how big the velocity is, gravity can sort of be like a lasso, like a rope, keeping the moon close to the Earth, enabling orbits. All right, so this is the basics of gravity, and these are things which were known before Newton, but I think it's fair to say that thanks to Newton, many of these things were sort of put in a framework. Later, so Newton is around 1600s, and then later Einstein came along and he wrote down the theory of general relativity in 1915, or he published it then. And you should really see general relativity as sort of a correction to Newtonian gravity. But it turns out that it's a very important correction for black holes, because it does help us answer the following question. Let's say that you are actually on Earth. How massive should Earth be in order for me to be unable to escape with a rocket, or even to make light not be able to go away from Earth? So these questions were apparently already sort of, people were already thinking about this every now and then. In the 1700s, this is some scientists from the UK, and this is the famous Laplace. But it wasn't until Schwarzschild, just after general relativity, that we got the current model for black holes, for things which can be so massive that a rocket cannot escape. Schwarzschild actually told us that precisely how much mass one needs in order to be unable to escape the clutches of the gravity of Earth. One thing Schwarzschild showed is that that will create a so-called event horizon. That's the thing you can enter, but you can never leave, like in the song of the Eagles. And but so not even light or rockets can escape. And actually, a sort of weird, funny fact about Schwarzschild is that he was actually a commander in the trenches in the First World War when he published his theory, or his solution to the black holes, and he died 4 months after it got published because of a allergic reaction of his skin. But the answer Schwarzschild would give is, if you want to form a black hole the size of the Earth, so it's black because no light can escape, nothing, you would need to make the Earth 10 billion times heavier. So this would be approximately 1,000 times the weight of the sun. So to sort of put this in a more graspable, I guess, Icelandic comparison, it's the sort of the weight difference between a human hair and a Arctic Toyota Explorer times 1,000. So it's really an incredible mass density you need in order to have a black hole. You could also sort of turn the question around and say, okay, I just have the mass of the Earth and I don't want to add more mass. How much do I have to compress the Earth in order to create a black hole, to have this immense high mass density? And it turns out that if you push it all the way to the size of a pea, then that is actually the first time that you would get an event horizon, a point of no return. All right, so Schwarzschild told us that there are black holes, but something else came along with the ride, namely a singularity. So in the middle of a black hole, as predicted by Schwarzschild, it turned out that there is infinite curvature. Space-time sort of breaks there. And one of the implications this has is so-called geodesic incompleteness. So what is a geodesic? So a geodesic is a path one travels when one is just falling. So if I'm, if I just jump out of a rocket, or if I'm a moon hovering around. And what people sort of like about the idea of general relativity is that it should be geodesically complete, meaning that if you live forever, you can just follow geodesics forever, wherever you go, whenever you go. However, if a geodesic crosses a singularity, really it seems like space-time stops. There is a problem, and you cannot continue on your geodesic. And this is something which people didn't like, and that's why these solutions were not really taken seriously. It was like, oh, this is some nice mathematical curiosity. And like tens of years later, Oppenheimer and Schneider, so this is the famous Oppenheimer from the atomic bomb, notably, wrote a paper, 1939, in which they showed that if you take a very, very massive star, which is collapsing, that one actually forms a black hole, as predicted by Schwarzschild, including a singularity. However, so this paper went unnoticed initially, well, due to historical events. But furthermore, when people in the 60s started to observe the universe around us using for the first time, beyond just normal light, radio waves as well, people started to realize that, okay, there have to be super heavy things, so these black holes might actually be not so weird. However, people still didn't like the singularity, and they sort of argued that the mathematics which Oppenheimer and Schneider used was a bit too symmetric. Namely, what they took was a very spherical star, and they let it collapse very spherically. So people were saying, yeah, probably these black holes, these things might be sensible, because we might need them to explain certain things we see. However, yeah, the singularity thing, that that's probably some mathematical hocus pocus going on due to the high amount of symmetry. And it was in the 60s that was actually shown to be wrong by Roger Penrose. So in 1964, he published a paper called Gravitational Collapse and Space-Time Singularities, in which he showed that basically what he did is he sort of departed from the spherical symmetry used by Schneider and Oppenheimer, and he showed that indeed black holes can form, and moreover, independent of how they form, a singularity will come along for the ride. So to get a bit of a flavor of what it is that Roger Penrose did, it's important to introduce the concept, well, it's actually a concept he introduced, of trapped surfaces. So he showed that basically gravity, if there is enough mass around, can be focused as sort of a lens, and by that attracting so much, having so much attraction that nothing can really escape. And to get a better picture for this, it's important to realize one of the important building stones of general relativity, and that is a light cone. So in general relativity, one moves in a light cone. So everybody would be sitting here, everybody has their own light cone around them, and if you move up, that's time, and this is space. And what a light cone tells you is that basically you cannot, if you move through time, there are places in space where you cannot go to because you're bounded by the speed of light. So light will always go like the edges, and you cannot go beyond that. So you always move in a light cone. And we're going to use that to sort of give you a flavor of the idea of the trapped surface in the following figure I'm going to show you. And it might be a sort of a scary figure, but I'll talk you through it, and it's actually a revamped version of a picture which Roger Penrose had in his original paper. So this is the figure. All right, so it's important to see that there are here all these kind of light cones all around, and time is moving upwards, space is orthogonal. So you start with some matter, and despite the fact that it's drawn very symmetrically in here, it could be super jittery. So it could actually be, well, a quite generic matter contribution. So what happens, so you have a collapsing star, a very heavy star, which starts to collapse under its own gravity. And you can see that things start to pull together here. And at this point, you're still able to send light signals out to people far away. But at some point, during this collapse, you'll inevitably reach the point where you cannot, even if you do your utter best, cannot send light away anymore. It will always be trapped into a certain surface. So from this point on, there is actually a trapped surface. And since the trapped surface is formed independent of the type of matter you have, it will show that all the mass will focus here together and create a singularity. So the thing which Penrose did was two-sided. On the one hand, he showed that it's very sensible in the theory of general relativity to have black holes appearing. And on the other hand, he showed that we better have to come to terms with the singularity. As we interpret the singularity now, it actually shows us that that is the point where we cannot trust general relativity anymore. We need something better there. So to come back to the words of the Nobel Committee, Roger Penrose got the Nobel Prize for the discovery that black hole formation is a robust prediction of general relativity. All right, well, of course, it's only best if theories can be verified in nature. So that this brings us to the other two laureates of this Nobel Prize. So now we're going to ask ourselves, how can we actually find the black hole in the wild, and where do we have to look if we want to find such a black hole? So of course we're going to use the laws of gravity here, and let me show you our solar system. So here you see the sun and there are various planets orbiting around it. If, however, I were to turn off the light of the sun, the situation would be like this. And if I were to study the orbits of Mars, Earth, Venus, and Mercury, I would be able to use gravity to actually compute the mass of the object sitting here and the location. So that is roughly what we're going to use as well to when we look for black holes in the wild is we're going to look for objects which are orbiting a seemingly empty point in space. So that's the way we're going to find it. So now where can we actually find these black holes in the wild? Well, a very good candidate turns out to be the center of our galaxy. So just to give sort of a perspective of where that is, so we are over here on the Earth. Earth orbits the sun, and that together is the solar system. And the solar system spirals around this thing called Sagittarius A star, which is probably a black hole. And that's also the ultramassive object which the Nobel Prize talks about. So what we are interested in is we are gonna have a look all the way from here, 26,000 light years further into the center of our galaxy. So 26,000 light years, 1 light year is the amount of distance light, light travels in 1 year. And for instance, the distance between Earth and the sun is 8 light minutes. So for convenience, we can also express these distances into astronomical units. So 1 astronomical unit is roughly the distance between the Earth and the sun. So this distance is 1.6 billion astronomical units. So what we're going to do is we're going to look 1.6 astronomical units away from us at some area of interest, which is about 10,000 astronomical units of width. So to get a better feeling, so that's where we can find a black hole. But to get a better feeling for these absurd distances, I have prepared the next slide. So here, we're here in our solar system, and we're going to peer into the center of our galaxy. So remember, this is 1.6 astronomical units away, and sort of the width of the area of the region we're interested in is only 10,000 of astronomical units. And this is sort of the same as we would climb up Hallgrímskirkja, and we would try to study the structure of a pea that somebody left on stake on Esja. So this setup. So this is about 10, 20 kilometers away. And we're standing on the Hallgrímskirkja, and we're trying to sort of look at the structure of the pea. So is it that easy? No, of course it's not, because, you know, there will be, the sun will be annoying us, or the moon, or it will be light, or it will be night. And generically, there's a lot of stuff in between us. And that brings us actually to the story of Gensel and gas. So how to study really the center of the galaxy? So a little bit of history. So from 1918 on, we know due to Shapley, which was an American astrophysicist, that there is actually a center of the Milky Way. And from the 60s on, due to radio wave astronomy, mostly, people started to suspect that there was actually a black hole in the center of our Milky Way. And from the 90s on, the groups of Gensel and Guess separately committed to study this center. So Gensel used the European Southern Observatory, ESO, which is in Chile, and Guess used the observatory, US observatory on Hawaii. So it's really cool that they both used like an entire, that they were working, that they actually support each other's results. So there are two big problems which you have to sort of, well, I mean, overgeneralize, there are two big problems which you have to overcome. So one of them is the clouds of stuff between us and the center, right? If you're at Hallgrímskirkja and you look at the P, there's a lot of stuff in between us. And also, we, factually speaking, live in like almost a 100 kilometers deep sea of atmosphere. And that makes like a lot of stuff very blurry. So how to overcome this? So the first problem can be overcome by studying the infrared spectrum. people already started to experiment with that, but it's really from the end of the 80s, beginning of 90s on that people really were building infrared spectrum telescopes. And this infrared spectrum basically is a different wavelength of light. So you go away from the visible light and you get this, and it turns out that all this murk between us and the center of the galaxy is, well, has a different way of absorbing the infrared spectrum, as you can see from the differences here. So this would be using light, and this is the infrared spectrum. So you can already see that you can see a lot more here. So then you also have the problem of the fact that you have the atmosphere. And a thing which was also, well, really started to flourish from the 90s on, also due to the advent of computers, is adaptive optics. So what is adaptive optics? So one can think about it in the following way. Let's say that there is some known thing here, so some known star or some laser guide star of which you know what it looks like. So its light goes through the Earth's atmosphere, it's distorted, and then it comes onto a mirror. But because we know what the light of the laser guide star or some real guide star is, we can correct the mirror. And real time, we're gonna correct the mirror, which sits in the telescope as well, such that we can correct for the smudginess of the Earth's atmosphere. And what comes out is this. So this is Neptune without adaptive optics, and this is Neptune with adaptive optics. So it's really these two great feats of technology which have helped a tremendous amount with trying to find out more about Sagittarius A star. So, all right, let's dive into well, what it really looks like there around Sagittarius. So a closer look. Remember, this is where we are, our solar system, and we're like, what is it, billion of astronomical units away, and we're gonna look at a 10,000 diameter area, 10,000 astronomical units area of space in here. So we're gonna blow it up, and it looks like this. And you see all these stars, so S1, star 1, etc., flying around a seemingly empty part of space. Now, let's zoom in on this S2 or SO2, S02, as one of the groups would call it, because this is a very special star for two reasons. One of them is that it gets extremely close to Sagittarius A star. And the other thing is that it was already started to be mapped in 1992, and it has an extremely short, it goes extremely fast around, namely only in 16 years, which is very short. You would say, okay, well, 16 years is quite long. But if you compare it to our solar system, we go around in 200 million years. Which means that the last time that the solar system was at this approximate location, there were still dinosaurs jumping around, and Iceland wouldn't even physically exist. And from all these measurements, so the perihelion, so the closest part to which here is 125 astronomical units. And furthermore, from studying all the orbits of all these stars, they have found up to a very close precision that the object here at Sagittarius A star has to be 400 million solar masses. So remember, when we took the Earth and when we said be a black hole, it needed to be around 1,000 solar masses. And this is 400 million solar masses. So this is an ultra heavy object, and it's most definitely a black hole. However, there have to be done more measurements to be exactly precise, and that's also why the Nobel Committee probably chose to sort of hedge their bets, and that's why the Nobel Prize is given for the discovery of a supermassive compact object at the center of our galaxy. But I think it's fair to say that these people really showed that our entire galaxy revolves around an ultramassive black hole. All right, so this brings us to the concluding slide, which is sort of a weird slide since I put a lot of words on it, and I put a little movie on it, which I think you should really see. So this is the Milky Way as observed from us. So the first part, which is like it's 1 minute, is just zooming into like telescope images. Then the second part is a sort of computer animation of the center of our galaxy with notably S2 whizzing around Sagittarius A star. And then the last part is, well, I think a simulation of what a black hole might look like. But yeah, I'm going to show you, and this is, by the way, this is made by the ESO, so the European Southern Observatory. So while we look at this, I'm gonna just say what the summary. So I think that this year's Nobel Prize really highlights the synergy between experiment and theory. And well, it's really the pioneering work of Reinhard Genzel and Andrea Ghez, which has led to, well, a new generation of very, very precise tests of general relativity. And most likely these measurements will also be able to provide clues for new theoretical insights. So that you have on the theoretical side, on the observation side. Then on the theoretical side, it's really Roger Penrose showed that black holes are a direct consequence of general relativity, but also that, so yeah, this is this is what happens really at the center. And these are actually images of S2 whizzing around and its S friends. Anyway, so Roger Penrose also showed that there is a singularity there. And people say about this singularity that it is actually the seed of destruction. So general relativity sort of has sown its own seeds of destruction, which is extremely cool because it means that it shows that if we want to see new physics, basically the combination between general relativity and quantum physics, then we really have to study the black holes, or most notably, the inside of black holes. So the universe has many secrets and surprises left to be discovered. And with those words, I'd like to thank you for your attention. Tack för er ögon.